Core to cloud. That's the important thing I need to do. Core to cloud. Okay. Yeah, we barely touched the surface. So let's go back here. Do you guys see my screen?
Yeah.
Good. I can't annotate on this, which is annoying, but that's okay. That should be fine. So module four. Um, yeah, briefly, we're gonna go over. Oh wait, I can't annotate it because I can use that. Let's go. Okay, perfect. Okay, we're locking in. Well, let's lock it. All right. So yeah, octet rule is really important. Because yeah, there could be a lot of questions on that. Polarity is really important. So just using the electronegativity values on the reference table is really important. So yeah, ionic compounds, those are this question, like they're gonna be metals and whatnot and ionic compounds and salts that are gonna be in the questions and you're gonna have to know whatever. And this also goes into like, the solubility rules stuff. I'm not sure if it's in this chapter or next chapter or whatever chapter, but yeah. If there's any questions you want me to go over, like um in the slides or just in general, let me know. But yeah, something like calcium fluoride, right? Fluorine has a -1 charge. Sorry, that does not look like a one. Um, and then calcium has a +2, right? So then you crisscross applesauce and you get calcium F2, right? So nice little trick there, right? So covalent bonds are sharing of electrons. That's the big takeaway with covalent bonds. And this is the whole crux of this chapter. How do we make, what's the geometry of these things, right? So yeah. So this is like a polar covalent bond. This is gonna be more important next semester when you guys learn about intermolecular forces. But for now, you just need to know that like the polar bond, like the intra forces, like the forces in between atoms in a compound, right? Like polarity versus nonpolar, and whatnot. Yeah. This could be like a question that's just like true or false. What is true about molecular compounds, right? Or something like that. Which of the following is not true about molecular compounds, right? And so yeah, there's definitely gonna be questions like these kind of things, which is like increasing in polarity. And I'm telling you, just check the reference table. Check reference table. My handwriting is awful, but that's okay. Predict the chemical formulas for the following. Yeah, this is not gonna be on the test. This probably wouldn't be on the test, but something like this probably would be. All right, so nomenclature. Anyone have any questions so far? Okay, you guys are all vibing, I see. Okay, it's good. I hope you guys have wonderful holidays and breaks and whatnot. Okay, anyways, so binary compound, yeah, let's get, I think all of this is pretty self-explanatory. Yeah, naming things is just like really important. And um, yeah, if anyone is like having trouble with naming things, please ask me because I'm probably gonna just go by them like quickly. Most of the time, it's just like with ionic compounds, it's like the metal with the non-metal, and usually you just add the "ide" thing. With the polyatomics, or we haven't gone to that yet. These are the exceptions. These are important exceptions. They're definitely going to be on your test, and he's definitely going to like put like zinc chloride, right, in like a word form, and you're gonna have to know it's ZnCl2, right? Or silver nitrate, right? You're gonna have to know it's AgNO3, right? Yeah, with polyatomics, you take the metal and you take the polyatomic name. So this is chromium 2 sulfate. The reason why I knew it was chromium 2 is because chromium is a transition metal. I know that because it's in that like big, it's in, where is it? It is, it's in this big box of like things, right? So typically when you see metals in this like middle area, right? That's a trend that they usually are transition metals. There's a couple exceptions, but he's not really testing you on the exception. The only exceptions that he is testing you on is something like what's it called? Zinc, silver, and palladium. I believe that's what he said over here. Where is it? Cadmium. Sorry, my bad, guys. Cadmium. Sorry. So those are the three exceptions. Yeah. So with these, it's just you take the metal with the non-metal, or sorry, metal with the polyatomic name. So chromium 2 sulfate, barium hydroxide, cesium cyanide, right? Ammonium bromide, and then silver nitrate, right? Like I mentioned earlier. Actually, I'm tutoring some kids in my high school for like chem, and they have these questions with like hydrates, and they have to find out the percent of water in the hydrate. I don't think you would ask that kind of question, but it's just something good to know, right? Hydrates are just things that have water in its compound. I think you guys did an experiment on that in your lab. I'm not 100% sure. I forgot. But now we're going on to covalent things. Does anyone have questions about that? About anything that I just went over? All right, I'm gonna keep yapping. So then yeah,
I
binary
had a
covalent
question.
thing. Yeah, what's up?
So, would he ask any of the Latin names?
Lab stuff?
The Latin names for like the Farius and Fair.
Oh, no, not really. That's a more older kind of way of talking, right? So it's not gonna say like ferrous or ferric. It would be like he would say iron to chloride or something like that. He never uses ferrous or ferric. But
Okay, thank you.
that's actually a good thing to kind of know, only because like for acids, which we're about to get into, like usually the us is like less and ic is more, which is what we're gonna get into soon because it says here naming acids. But anyways, yeah, with naming covalent things, covalent binary things, right? You would do nitrogen dioxide, right? Basically, you have these prefixes, and typically what you do with the prefixes is you never use mono for the first one, and yeah, you always end this with the "ide," and that's pretty much it. So it would be nitrogen dioxide, dinitrogen monoxide, sulfur hexafluoride. All right. If you guys are confused about that, please ask me, because yeah, I don't want to just be glossing over this and whatever. We have three modules to get through, so I'm gonna try to speed up a little bit. So yeah, with acids, it's a little different. So with acids, if it's just with the element, you would say like hydrochloric, right? So like a common issue that some people have on like knowing acids is a common like example of a confusing thing is like H2S versus H2SO4, right? For this one, this is hydro um, sulfuric acid, right? But this one, it's sulfuric acid. So like there's a little bit of a like a like a confusing thing. Like why is this sulfuric acid and this one's hydrosulfuric? And it's because of these rules, right? So like basically anytime it's bonded with the element, you say hydrosulfuric or hydrochloric, right? This is hydrochloric. This is hydrobromic. This is cyanic, right? So that when it has a polyatomic, you skip the hydro and you just go to the the polyatomic. So for this one, it's cyanic acid. For this one's nitric acid, right? And then this is where I was talking about earlier with the us, right? The us, right? Anytime there's a ite, or frankly, if you know that this one's nitric acid, right? Anytime the oxygens change, that's like the big takeaway. That means that the strength of the acid actually decreases. And that's why instead of it being an ick, it's an us, right? It's like going from a sharp sound to like a wavy, oof, like whatever. Yeah, so it would be nitrous, right? Nitrous acid. Sulfuric, sulfurous. This is perchlorous acid. Um, yeah, does anyone have questions about that? Because if not, then I'm gonna keep going. So we're getting into some of the nitty-gritty stuff, right? Lewis dot diagrams. I'm not gonna really spend much time on this because you're gonna be asked to rarely would you ask I mean, I don't know. Lewis symbols. You're not gonna be asked for like ionic compounds. Ionic compounds are fairly self-explanatory. There may be one or two questions. There probably wouldn't even be. There might be one. I don't think it, I don't know. I don't know. Just be yeah, if you know it, you know it. If you don't, you don't. So you should know it. So calcium plus two, right? Chloride would be one, two, three, four, five, six, seven, eight. It's a direct transfer of electrons, so this would be -1 and this would be 2. Okay? Yeah. All right. So yeah, that's how you do Lewis dot diagrams with ionic compounds. I'm sure that you guys are all like chilling with that. So then yeah, now this is the octet rule and the duet rule, right? The duet rule is just with hydrogen. So hydrogen only likes to have two bonds, right? So let's say this is CH, right? this is like this hydrogen satisfied, right? But like with methane, so this is methane. So this would be CH. Oh gosh, let me redraw that. Sorry guys. CH H H H, right? So something like this, right? This is duet. This is the octet rule. All right. Hope you guys are following along. All right. So does anyone want me to go over this or anything like that? Or are we chilling with this? Okay. All right. I guess we're chilling with this. There could be questions where it might ask like how many lone pairs are on whatever, or how many, is it a triple bond or a single bond, which is the better one, right? Or so it's important to know. Carbon monoxide is a pretty good one. This is C and O. It would be like that. That's like the best confirmation or best structure for this. Okay. So yeah, Lewis dot diagrams can help anticipate bonding. Um, yeah. Do you guys want me to go over any of these? You're not gonna need to know what this molecule is. Um, yeah. He was just doing this as an example to explain some things. Okay. All right. So this is where it gets a little bit tricky with polyatomics. I'm just gonna do one. Let's just SO4 sulfate. Yeah. So sulfate would be, so how many electrons are in S? S has 6 electrons. How many electrons is in oxygen? That has 6 electrons. Is anyone confused with where I got these numbers from? No? Okay. This would have 2 electrons because there's a -2 charge, right? And so it'd be 6 plus 24, which is 30, 32 electrons, 32 in total, right? So, sorry, I should do that. So whenever you do this, you want to go through this thing and you want to be like, you want to first draw out with the single bonds and see like, okay, can I satisfy the octet rule, right? So that's what I like to do. So I'm adding the 6 electrons to each one, right? This does satisfy with the number of electrons I have, and yeah, it satisfies the octet rule. However, the proper structure with this, because it's hypervalent, or is it hypervalent, or I don't know what the term is. I'll go over that second soon, but like basically sulfur is in the three, like the group, like under the period 3, right? And so because it's under period 3, it has access to its d orbital. And so because of that, it would be preferable if um it gets, well, plus the oxygen wants to have 2 bonds too, right? And so because of that, it's preferable for 2 of these oxygens to give itself like a double bond like this. All right. And that's where the -2 charge comes from. And as we're going to get into this formal charge, right? This would be 6 minus 4 because of there's 4 little small electrons minus 2. So that's 0. This would be 0. This is 6 minus 6 minus 1, which is -1. This is -1. And then this one would be 0. And that's this the sum of the charges is equal to the charge of the sulfate ion. So something that's pretty nice to know. All right, so I'm kind of jumping ahead with this module because there's a lot to it that you could talk about. So yeah, there's some that have an odd number of electrons. I don't really think I need to spend a lot of time on that because I don't think he would ask something like that. Okay. Electron deficient, that's something he would probably ask. So something like boron, uh, maybe beryllium, but yeah, mostly boron. It would be like it would only want to have 6 electrons. So that's a little bit weird. So electron deficient and hypervalent. I was right. Okay, so like something like sulfur and phosphorus. So that's a very easy example. So PCl5, right? PCl5 is it bonded to 5 chlorines. Okay. And then the other one would be sulfur hexafluoride, where sulfur is bonded to 6 fluorines. Can anyone tell me, do you guys know the structures of these? The geometry of this? Would anyone like to participate in that? Does anyone remember the geometry? of this guy or this guy? Does anyone know? Okay, that's okay. As we get into this, this will be trigonal dipyramidal, right? Because that's the one with 5 electron domains. And then this one would be what's it called? Octahedral. Okay, we're gonna get into that soon, so don't worry if you don't know it. So I kind of jumping the gun with formal charges, but formal charges is really important. Um, I don't really know why like this. I don't really go by this formula. I usually just do formal charge um equals bonds or yeah. Actually, no, I think this is what number of bonds. I don't know, and I don't know what they represent. I'm not. I'm not sure what. So valence electrons, right? Minus bonds minus specific electrons. That's essentially what it is. Yeah. Does anyone want me to go over any sort of examples with formal charges or anything? Okay. So, yeah, formal charge is really good because it can find the most favorable resonance structure. So that's really important. So, what's it called? It's like nitrate. Um, actually, I mean, nitrate is like not really something that would show formal charge and how it's a predictive power, but we all like went over this example of how this forms a -1 charge and it has resonance with something like the other one with like the electron moves from there to there. So then it's like that, right? And then it has like it has 3 resonance structures, right? So then you would say that it is yeah, they have resonance structures. They're all like major contributors to it. But like that's what he showed here. They're all 3 resonance structures. Okay. Oh, I'm sorry, guys. I'm losing steam here. Anyone has any questions or comments, concerns, or anything? Okay. Alrighty. That's it. Okay. Um, yeah. So yeah, so there's definitely gonna be a question or two on resonance on your test because this is a pretty good topic that could be tested because it's a little confusing and it's a thing that is good to show like if you know and it tests a lot of things. It tests your ability to write Lewis dot diagrams, it tests your ability to time formal charges, it tests your ability on yeah, it just yeah, it tests a lot of the stuff we already went over. So this is about molecular structure and polarity. This is something I learned in Orgo, like the R and S configuration. You don't need to know that now. I'm just pointing it out because it's kind of cool to see that. So this is the Vesper model. This is really important because this can help be a predictive power. Like this is something that helps predict the formal, like the polarity of molecules. And so yeah, he talks about it in regions of electron density, right? So without any sort of lone pairs, 2 regions of electron density, right, connected to the central atom would be linear. An example of this would be CO2. Okay. Something with a trigonal planar structure, right, would be something like uh, borium boron fluor trifluoride, right? Or another thing would be formaldehyde, which would be something O, like with a H, like this. That would be trigonal planar. Something like this, tetrahedral, CH4 is good. SH4 is also good, or not SH4. Silicon, tetrahydride's good. Yeah, something with 4 electron densities. This is without any sort of lone pairs. None of these are with lone pairs. This is with 5. This is PCl5. This is the one I gave, and then S5, F6 is octahedral. So these are stuff without any sort of lone pairs, and everything with the lone pairs kind of like branches off of this, right? So, um, Yeah, electron arrangement's really important. Yap, 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 yap. So he's gonna get into this now. So with um linear, right? So this is with the two electron densities, right? This is with three electron densities. This is also with three electron densities. However, two of them is with an atom and one of them is with a lone pair. And so example of this would be sulfur dioxide. So this is trigonal planar electron arrangement because there's still three electron domains. However, the molecular geometry would be bent. And so something like this would be S, right? Sulfur dioxide. Can anyone tell me the valence electrons of sulfur dioxide? Anyone? Man, you guys went through COVID, right? Like you guys know like the silence is really killing. Oh, it's now I feel like now I understand how the teachers felt. Okay, anyways, so it's 6 valence electrons for sulfur because it's under oxygen, plus 2 times 6, which is 18, right? So it's what? S O O 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, right? So there is what's it called? There's 16 electrons, so you put a double bond. You put a lone pair there. That's sulfur dioxide. And so when you see this kind of molecule, right, there's a lone pair, there's two, what's it called? Oh, atoms that it's bonded to. So you would say that this is electron arrangement of trigonal planar and it's bent. Okay. Something like this. So now we're going into the tetrahedral. Did anyone have questions about the earlier stuff? If not, then I'll keep moving forward. All right. So this stuff is pretty self-explanatory. So an example of this would be CH4. This is ammonia. That's a good example. And this is H2O. These are like the prime examples of whatever. Um, yeah. So NH3 would be something like this. Ooh, I should really write better. NH3 with a lone pair, right? That's trigonal pure metal, right? Something with H2O would be HOH with two lone pairs, right? So they have the same electron arrangement as methane, right? Methane would be something like CH H H H, right? There's 4 electron domains there. Same thing with here. There's 4 electron domains, but there's one lone pair and 3 atoms, right? So that becomes trigonal pyramidal, right? Think of like a pyramid, right? Same thing with this. This is now bent because there's 2 lone pairs and there's 2 atoms it's attached to. So that would be bent. Okay. So then now we're moving on to the big stuff, the 5 electron groups, right? I think the first two of these, like the linear trigonal planar, bent, and then tetrahedral trigonal pyramidal and bent, those are things you kind of need to memorize. And I think it's kind of good that a lot of the familiar molecules are this. But then how do you memorize the 5 electron groups? I have a great way of doing that, and it's through the mnemonic 3-2-T. Okay. So we have to, I think it's important to memorize like these like top ones, right? So this is tetrahedral, this is linear, this is trigonal planar, right? It's important to memorize the top like names, right? And then like kind of figure out whatever based off whatever. I have like a mnemonic, right? Where it's like 3-2-T, right? 3 atoms, 2 lone pairs, right? It's a T shape, right? So that helps me kind of understand whatever. Because if 3-2-T, if 3 atoms, 2 lone pairs is T shaped, then 4-1 has to be a seesaw because the other one has to be linear, right? It's kind of like that's the way I like kind of memorized it over the years I've been doing this kind of stuff. Um, but yeah, so yeah, this stuff, if you can't really use, if you don't want to use the mnemonic I gave, then you can just like memorize it, make like a Quizlet or something, and it should be helpful. Octahedral, right? This is now going into the octahedral stuff. Again, with the electron, right? This is lone pair, this is make a square pyramidal, and this would make planar. And it's important to note that like anytime it says pyramidal, it's a polar molecule. And anytime it says bent, it's also a polar molecule. And then anytime it says planar, it's a non-polar molecule. And anytime it's linear, it's also non-polar. So something to that those are really important things to know because how can you tell the difference between like something like um what would be a good example of this? I don't know. Hmm. Hmm. I don't know. Yeah, how would you be able to tell the difference between uh yeah, sulfur dioxide versus carbon dioxide? Um, right? Like using the electron arrangements and whatnot, it's important to just like figure out which one would be polar, which one would be non-polar, right? Um, because yeah, the oxygen and carbon would make it look like, oh, maybe it is polar or whatnot, right? So here's like a little summary of it all. And yeah, that's important. Does anyone have any questions about any of this?
Can you repeat what you said? You said bent and linear are wait, sorry, linear and trigonal planar are non-polar,
Linear
and then
and
trigonal planar.
yeah, anytime it says planar, it's non-polar. So trigonal planar is non-polar. Um, but it's when I say that, I'm referring to just a molecular structure. Don't get it twisted, right? So the electron arrangement, right? That's its own thing. The molecular structure, anytime the molecular structure is planar or linear, right? It is um a non-polar molecule.
And then the
Unless,
oh,
yeah,
and
sorry,
then the rest of them are polar.
and also the base stuffs like tetrahedral,
Okay.
linear, trigonal planar, right? And then trigonal bipyramidal, that's also um non-polar, right?
Okay.
Yeah. The only like exception to this is if in the like let's say in the like PCl5, like instead of it being PCl5, it could be like PCl4I, right? If it's PCl4I, then that what that means is that it probably there is some polarity difference because of that I. So like that's something to just know. Like that like first you figure out the molecular structure and then check the atoms that's in the molecule. Like is the um would they yeah, like is there electron negativity difference? And that's how you can like you look at the reference table for that. Okay.
Okay, thank
Yeah.
you.
So like also octahedral is non-polar. And then yeah, this is polar, this is non-polar. So that's good to know. Okay. All right, good. I'm glad that you asked that question. I appreciate it a lot. I want to help you guys out as much as I can. Alrighty, moving on. So, yeah, just a lot of blank pages for me because I didn't write notes while you guys did this. Um, hmm, okay. So, yeah, this is all just stuff that we've already gone over, and then now we're at the practice problems. All right, we're done with module 4. Does anyone have any questions about it? Anything at all? All right. I know I'm going through this fast. I know it's kind of annoying at times, but
So,
yeah.
what
Hmm.
on the test, if we asked to draw like a Lewis dot diagram, would like to see which one's polar or not, do we always draw one with the least formal charge, like the
You want
lowest
to
formal
draw
charge?
with the smallest possible formal charge. So like
So
for
even
example,
if it doesn't specify that, it's we always draw it that way.
hmm yeah. So like something like sulfur dioxide. That's a good example that I keep bringing up. Sulfur dioxide. Um, right. So if I were to draw that out again, so it would be SO2, right? 6 ounce electrons plus 2 times 6, right? That's 18 electrons, right? First thing would be something like this, okay? Where now there's while yeah, like there's this is a valid like Lewis structure, it solves like the octet rule and whatnot, the formal charge is not like fully there, right? This is a -1, this is a +2, this is a -1. Don't worry about how, like, I'm like really, like, I know, like, I practice a lot with this stuff, so that's why I'm quick with it, right? So then because of this, you would want maybe this one to give its of double bonds. So then it kind of disperses out the charge a bit. So this is a better structure than the one I just gave. So like always on the test, if it doesn't say draw it in an octet rule, then you do it normally. That's what I like. You do it with the minimized formal charge. Okay?
So what if you draw with like two double bonds with the O and the O on the other side?
Well, then if you draw it with, you could, yeah, you could, what am I saying? Yeah, you totally can. You could do that as well. Yeah, what am I doing? I forgot that as well. So you can do this as well. You're 100% right. So yeah, this is a way better thing than this. So that's good. All right.
Would that be polar?
This would be polar because this bent, right?
Okay.
So it has a lone pair there. It has two atoms, right? So we know from the chart, right, that is um a I don't know the AXE, whatever nonsense, but 2, 1, right? That's gonna be bent, right? So I drew that wrong technically. So it should really be looking like this, like that. All right,
Okay.
good. I'm
Thank
glad
you.
that, yeah, no problem, no problem, Bob. All right. So this stuff, he yapped a lot in this lecture. This one is like, this is pretty important. There's definitely gonna be some sort of like molecule on your test where it's gonna like have like all these like different carbons attached to each other and whatnot, and you're gonna be asked like find the sigma bonds or find the pi bonds, right? Um, and so basically it's all about just kind of knowing what does sigma bond mean, what does pi bond mean, and also knowing the sigma sign, right? Sigma looks like this, okay? So on the test, if you see this sign, that's sigma, okay? He usually, I remember on one last test, he used that sign instead of like saying sigma. So then I got a little confused. So it's important to just know that. So how many sigma bonds would be in this random molecule that I just drew? All right, there would be, right? If we were to count this, sigma bonds are just simply single bonds, like single bonds between things, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so there's 11 sigma bonds in this. All right, so that's basically what you need to know for that. Pi bonds are a little different. Pi bonds are when there's a double bond or a triple bond. So something like looking at nitrogen like this, right? How many sigma bonds are there? There's one sigma bond and there's two pi bonds. And yeah, he likes to use these symbols instead of saying pi or sigma or whatever. So yeah, this is a pi bond. And then there's also a sigma bond there as well. Okay, so he went over this stuff. So there's gonna be like some sort of molecule like this, or like a bigger molecule, and it's gonna ask you to figure out all the sigma bonds, all the pi bonds, and you're gonna have to know whatever. So that's important. All right. So this is where everyone probably like got really confused and was like, what the hell are we talking about? Hybridization. So hybrid orbitals are, yeah, they basically are, I don't need to explain it like super in depth, but basically, like, yeah, he gave a bunch of things for this. So like SP like thing would be something like ethene or ethine. What am I saying? So it'd be, what's it called? Or what a, well, no, guys, that this is a wrong thing I just drew. I'm so sorry, guys. Hope I didn't confuse you guys. So it'd be something like this, right? This is ethine. Okay, so this is a sp carbon. How do I know that? Because it's connected to two atoms. That's basically like the bottom line with sp. Um, like hybridization, right? To figure out the hybridization of one carbon, you just count the stuff that it's connected to. And also you may also need to count the lone pairs. you just count the electron domains. So there's 2 electron domains in this, so that's sp. Yeah, typically a good thing to also know is that sigma bonds are the hybridized orbitals. Those are the things that are hybridized. Pi bonds are unhybridized. That's just something to maybe know. He might ask a question about that. Okay, so the sp2 would be something like what's it called? Something like this, something like formaldehyde. So this is sp2, right? Even though there's a double bond here, it's not about the double bonds. It's about how many things is the carbon bonded to, right? So for here, it's bonded to 3 atoms, so that's sp2, right? I'm just simply counting the exponents, right? So S would technically have like 1 exponent, and then P would have 2, so that's 3 in total. So there's 3 things. All right, sp3 is a little bit similar, right? sp3, there's 4 things. So methane is sp3. Right? So because it's sp3, yeah, there's just 4 atoms it's bonded to. And so with these kind of things, all these things, you can predict geometry with it. Same thing with sp3d and sp3d too. You can predict geometry in that. So basically, if you like, let's say, let's talk about ammonia real quick. He wouldn't ask you to find the hybridization of ammonia, but just off the top of your head, right? I just didn't go over this, but like basically with the lone pair, that counts as an electron domain. So there's 3 atoms and a lone pair. So that's also sp3, right? So that can tell you about the electron arrangement and geometry of this, right? The electron arrangement like has to be similar to tetrahedral, right? And that's kind of what happened. Like trigonal pyramidal is similar to tetrahedral. That's why it's in the same electron arrangement. It's just because of that lone pair, it changes and becomes trigonal pyramidal. So that's just something to know. Same thing with water. Water, you wouldn't ask this on the test, but like this is also sp3 hybridized, the oxygen, because that oxygen is it has 2 lone pairs, right? And then 2 H's. So it's about the electron domains that's around the central atom. Okay. And so yeah, it helps predict the overall geometry of an atom or the central atom. So like something here, right? Like we would expect the geometry of this carbon to be planar, right? It's trigonal planar. How do I know that? Because it says it's sp2 hybridized, and because there's 3 electron domains, we would think that this carbon would almost match like trigonal planar. So like kind of putting together the last module with this one, that's basically like the bottom line with this thing. And so like this is essentially the also like something you're definitely gonna see, something where it's gonna be like asking, figure out all the hybridizations of this and like fill it in thing. Okay. I hope I'm being clear with you guys. I know I'm like I'm a little tired today. I'm sorry guys. But yeah, so this would be sp3 because there's 4 things, right? sp3, this is also sp3, this is sp3 as well. This, however, is also sp3. This is what we showed ammonia. This is sp3. This is sp2, and then this is sp3. So it helps like kind of predict geometry and whatnot. And it's just, yeah. Does everyone understand where I got all these things done? Or any questions about this module?
No.
Nice. Okay, sounds great. And then yeah, look into module 6, and then yeah. So key dookie. So module 6, now we're getting into more of the math involved. And so like with this stuff, it's fairly self-explanatory. This is important, knowing the diatomics. A little good trick to know is that this is like a backwards L. So maybe think of like your SI, right? My name is Luke, right? Backwards L, right? Diatomic, okay? Just maybe try to associate that if you have trouble. Another way to associate it is like an acronym. So I always use Hunkelbrief, Hunkelbrief, sorry, Brief. That's my acronym. There's a bunch of other acronyms if that doesn't work for you. And then yeah. So empirical formula, that's important for future math problems, and then isomers, that's kind of important. there may be a question that's like, which molecule represents an isomer of this, right? So that might be a question like that on your final. Okay. So then, yeah, we're moving on to some formula mass stuff. So yeah, formula mass units are for like ions, right? Formula mass units is pretty important. Formula mass, some of the average atomic masses of all, some of the average atomic masses and all the atoms present in the substance. Yeah, I don't know. I always use a molar mass. I don't know why it says formula mass. That's weird. But yeah, and then there's 1 mole. And so yeah, the mole is really important. I kind of illustrated this in the sessions, but basically the mole can relate to mass, right? It can relate to molecules, and now we know what the gas laws. At STP, I'm just going to put at STP, it can relate to liters. So this kind of thing is really important for like a lot of different conversions and stuff like that. And that's kind of the the whole gist of the mathematical portion of chem. Whoa, I can do that. Okay, that's cool. Yeah. So yeah, knowing how to write molar mass to I don't know if you guys did this in like high school chem. It's like my teachers used to call it GFM all the time, but I've gotten used to saying molar mass, right? And so a good thing to know is that molar mass is in grams over mole. For every X amount of grams of a substance, there's 1 mole of that substance. That's the relationship. And so you can technically flip this over, right? So there's X amount of grams, there's 1 mole. Sometimes you can do 1 mole over X amount of grams, right? All these are just relationships, right? It's the same thing as me saying 12 inches for every 1 foot, right? Versus 1 foot over 12 inches, right? It just depends on the conversion that I'm doing. And so, well, that's kind of like my little gateway into like trying to do some math problems with this. All right. Do you guys want me to go over any of these sample problems? Anything? Enough time? Okay. So yeah, determining empirical formula and molecular formulas, right? So yeah, this is a pretty important thing because mass of element over mass of compound equals mass percent, right? So something like calcium carbonate, right? If you find them, actually, mass of element. This can depend on whatever. Yeah, you can do a bunch of things with this. Yeah, but basically, yeah, with this kind of thing, this formula, it's important for yeah, it's just important. There's gonna be some questions with that. Some questions with mass percent where you just have to calculate it. And then yeah. Oh. Okay. So does everyone remember how to do the percent composition stuff with this question? What is this compounds percent composition? So all you have to do is take part over whole, right? And times that by 100, right? So there's 50.9 chlorines, grams of chlorine in this gram of substance, right? So this is the mass percent of chlorine, right? So that's the percent composition of chlorine within this unknown compound, right? You take this part, and you put it under this hole or over this hole, and then you get the mass percent of oxygen in the compound, right? It's it seems a little complicated when you first learn it, but then as you get to it, you get to realize like, oh, part over whole. That's essentially what I learned. Like it's fractions, right? So it's nice. And yeah, so does anyone want to go over percent composition or anything? Okay, this is an interesting problem. Instead of finding the percent composition and whatnot, it gives you one of the percent compositions and asks you to find the chemical formula of that. How would you do that? So basically, there's a couple ways you could go about it. I think one of the ways I would go about it is I would do something like I would find the molar mass of the mass of carbon within the molecule. So it would be 13 times 12.011, right? Equals, I don't even know, 12 times 13, that's 160. Wait, what? 144. 12 times 13. Is 12 times 13 166? No, 156, right? 156. Guys, please don't embarrass me. I'm sorry, guys. Please, 156. All right. Yeah, something amount, right? 156, I'll do some sort of thing where it's 156 over x equals 75.69 over 100. You know, use your graphing calculator, find the molar mass of the molecule, and then from there you can do some algebra, right? So if x equals the compound's molar mass, right? Then you could do 13, right, times carbon, right? Because that's the molar, that's 12.001 plus 18 times hydrogen plus like y times oxygen, right? And so we know molar mass of oxygen, right? That's 15.99. We know all these variables. If we calculate this from here, you can solve for y and get the number of oxygen in that thing. Okay. Yeah, does anyone have questions about what I just did here?
No.
Okay, sounds good. See you. Yeah, this is important. So basically, anytime you do empirical formula, you never really need a round or anything because it's about the empirical, like it's just a whole number. So, yeah. And also you want to convert these things from grams to mass, and then from that you divide by the lowest number of masses, the lowest number of moles. So for this kind of question, what are we gonna do with this? We're gonna do 38.85 grams of iron, 16.70 grams of oxygen, right? So the thing is you're supposed to divide by the molar mass of each of the atoms, right? To find the the empirical formula of this ionic compound, right? So what would be the molar mass of iron? Can anyone tell me what that is? If you guys have your reference tables out, because I don't have my reference table.
55.84.
55.85 grams per mole, right? And this one's 15.99 grams per mole, right? So what we'll see here, where's my graphing calculator? I have my graphing calculator. Let's see. Okay, well, let's use this. Okay, so I just pulled up my crusty dusty calculator. 55.85. Let's get something like 0.696, right? And then this one is really close to 1, 6.70 divided by 15.999, right? That would be 1.04, right? And then you would divide by the smallest one. So you would divide by this. 696, right? And you'd see that you get 1 here and you get 1.5 here, right? So when you see something that's like really close to like 1.5, you want to multiply it by 2. So the final answer would be Fe2O3. All right, so that would be iron 3 oxide. Okay, sounds good. Anyone have questions about what I just did there? There's definitely gonna be some sort of empirical formula question on your test, so it's a good thing to go over. Okay, so this is kind of a summary of what we just did. And then yeah. Does anyone want me to go over any of these questions? Okay, if not, then I'll move on to the molarity and units of solution. So as you know from the last test, like a lot of times there is going to be stuff with molarity. Molarity, right, represents the amount of moles of something per 1 liter of that solution. So, what's it called? Calculating molarity, it would be something like mole over liters, right? So in this question, you're just gonna convert this to moles, right? And convert this 250 milliliter solution to liters, right? We know that 1,000 milliliters equals 1 liter. Okay, and then yeah, same thing with this. Now what we're doing is we're kind of using this conversion to, you're gonna use the molarity to convert that. Obviously he taught you guys about like moles over liters, right? And this is kind of the formula that you want to plug it in. I'm gonna show you guys just like a little brief thing of how to like do the dimensional analysis of this, right? So for every 0.600 moles of NaCl, there's 1 liter, right? So this is NaCl, okay? And so to get rid of this liters, you have to multiply by liters. So you would have to convert this to liters. So it would be 0.5 liters, okay? Or 0.000, because that's technically the sig figs, right? So that would get rid of liters. And now you have just moles. And so now what you want to do is you want to use the molar mass. So I believe the molar mass of sodium is 22.99 and chlorine it's like 35. Is that right? I'll look here. It is 35. Okay, good. So 22.99 plus 35. Let's do that. 22.99 plus 35. And you get some sort of thing. I got a syntax error because I put the wrong thing in. So boom, boom. You get something around 58, 35.45. That's a better thing to put in. All right. Okay, 58.44. Perfect. So like I just showed you guys how to do a bit of dimensional analysis to solve this. I think it's a lot better to do dimensional analysis because of the way the test is structured. You guys are only gonna have like multiple choice questions, so your work really isn't done well. Like you don't need to show a lot of work, so this doesn't show a lot of work. As confusing as it may look at like at first, it's actually a faster method if you practice it. Dilution, I never even use this equation. I mean, you guys can use it if it helps you guys. Sometimes I get more confused with it. So I just kind of use dimensional analysis. And there's definitely going to be some question on your test with dilution. And so that's important. Mass percent and volume percent, I highly doubt there would be a question about that. However, I don't want to tell you something that might not be on your test or may be on your test. So I guess like just know the formulas of this, right? Mass percent is, I think it's all kind of fairly self-explanatory, right? It's part over whole, right? Part over whole. And then yeah, this is also kind of iffy. I don't really remember this on the final from last year, but I think one of the reasons why I'm also not giving you guys the final, is as you saw from the practice final I gave from last year, it's like really weighted to, it was really weighted towards module 8 and 9. And that's because we didn't have an exam 3 like you guys did. And so because of that, like yeah, it's not really a good representation of what your final will be. So yeah. Okay, and then parts per million, parts per whole, per billion, parts per million, right? I don't use this formula. I do something different. So I'll show you guys. So if I had 387 parts per million of what's it called? If I had, yeah, of like oxygen, right? Okay. What I can do instead of showing 387 parts per million of oxygen is I can just show, what's it called? 387 grams of O2 for every 10 mil, like that represents 10 million. Or sorry, not 10 million, 1 million. That's what 1 million is. 1 time 10 to the 6th is 1 million, right? That should be 1 million. And 2d6 is 1 million. Yep. Okay. So I like to always use these kind of formulas to like kind of like, what's it called? I'd rather show like the relationship than use these formulas. If you guys use the formulas and whatnot, that's good for you. And if it's better than what I'm showing, then do that, but I'm just showing like how I use it because I don't really, the formulas kind of confuse me a little bit. Okay. All right. So with that in mind, does anyone want to go over these sample problems or any practice problems? Hmm. Okay. So yeah, like that's basically the whole thing with module 6. So we went over module 4, that was about Lewis dot diagrams, molecular geometry. Module 5 was a little bit of an kind of module 4 part 2, where it talked about hybridization and sigma and pi bonds, right? And then now module 6 is getting into that math, right? And it talked about molarity, it talked about empirical formula. And so those things, all these things are fair game for your test. So if you can answer all the sample problems and practice problems from all these modules, then you should be good. Okay. Does anyone have any questions or anything? I know that was kind of draining, at least for me. Hello, everyone here. Hello, guys. I hope you guys are doing well. Yeah, does anyone have questions about anything? Any comments or concerns that you guys may have? Anything,
Um,
anything about, yeah?
you mentioned that you shared the practice final for like your practice final. I don't see it in any of the emails.
It was in, let me see. It was in one of the, it was right before your exam
Oh,
3.
yeah, I remember. Yeah, now I found
Yeah.
it.
So that's like, yeah, I sent the practice final from last year
Okay.
because I think that's pretty fair. Um, yeah, that was a pretty, I would say that was a pretty good representation of our final from last year. But however, like I said earlier, it's not a good representation of what would be on your final because my final was more on modules 8 and 9. Like it was, I think he said like 80% of the test was like module 8 and 9. And then the
Yeah.
rest was like whatever from the last stuff. So yeah. Okay. Anyone have any questions in general?
I have a question from exam 2.
Yeah, what's the question?
So the question says a substance comprised of zirconium and oxygen is found to be comprised of 74% zirconium by mass, and then we're supposed to
Mhm.
find the chemical name for the substance.
Okay, so let me pull up good notes and then I will do that question really quickly. Let me see. Start broadcast. Okay, so can you explain to me what the question was about? So it said zirconium and what?
And oxygen,
Oxygen, and what was the information about this?
there's 74% zirconium by mass.
74% zirconium by mass, right? So automatically we know from this that if there's 74% of zirconium, there has to be 26% of oxygen. How do I know that? Because if it's just zirconium and oxygen, 100 minus 74 has to be 26. Okay, so now what you want to do is you want to take these values and convert these to grams, right? Because if they're 20, if this is the mass percent by gram, like if it's mass percent, right? If this was 100 grams in total, right? This would have to be 74 grams and this would have to be 26 grams to represent the percentages, right? So now what you do is you take these grams of zirconium and these grams of oxygen and you divide it by the molar mass. So what's the molar mass of zirconium? Can anyone tell me what that is?
91.224.
91.224? Is that what you said?
Yeah.
Okay, and this one's 15.999. And then yeah, you would divide this out. So let's see. So zirconium would be 74 divided by 91.224. And I got something like 0.81119, right? It doesn't really matter how many things I round to. 26. Sorry, this might look confusing. Sorry, 26. Sorry, 26 grams of oxygen. That's good. 26 divided by 15.999. And that is 1.625. All right. So already I can see here that this value is half of this. All right. So that's just something to like as you get more like practice with this, that's how you see that. I mean, that's you get familiar with those kind of things. But let's divide it out to make sure. So we divide by the lowest one. So 1119 and 0.11811119, right? On the calculator, you can just use the exact numbers. You don't need to just retype the whatever like numbers, right? So here you get zirconium, right, would equal 1 and oxygen would equal 2. So the correct answer for this would be ZrO2.
I
right?
did that on on the exam, and I did the exact same steps that you did, but then it
Mhm.
says that the answer is zirconium 4 oxide.
So that's the little trick, right? So that's what we're talking about earlier, right? So I didn't know that the question was asking the name. So we know from the recent chapters, right, that oxygen always is going to have a -2 charge, right? And so if oxygen has a -2 charge, what charge does zirconium have to be in order to have it to be like for the like the formula to be ZrO2?
Plus 4.
Zirconium has, yeah, it has to be +4, right? And so on the test, right, while you did get this answer, right, the name for this, right, would be zirconium. I don't know if I spelled that right. I'm sorry if I didn't, but 1,4, like zirconium 4 oxide. And that's what I was talking about with the Roman numerals. Transition. This is zirconium is in the, if you look on the, I don't know if you know what zirconium is or where it's from. It's in the transition metal like area, right? And so unless it's not an exception, it's a fair thing for like it to be a, like he can use as transition metal. So yeah, so I think the important thing that we just learned is like oxygen always has a -2 charge. And so by doing that, you want to also figure out what the charge of zirconium would be. All right. Did I help you out with that?
Yeah, thank you.
Yeah, no problem. Does anyone have any other questions that you want me to go over? Anything at all? You guys want to look at my Orgo stuff? Yeah.
So the next session would be tomorrow.
Do you guys want it to be tomorrow? Or I was gonna do Wednesday, but what do you guys want?
I don't know, whatever is easier for you.
I'll probably do it Wednesday.
Mm. Yeah. Do you
Yeah.
have a final tomorrow? Do
What's that?
you have a final tomorrow?
I actually don't have a final tomorrow. I have all my finals Wednesday. So maybe it would be better for me to do Tuesday, but I don't know. I don't know. We'll see. Do you guys like, would you guys rather, like, I know that you guys are probably like swamped with like bio, right? Like bio's killing you guys, right? I don't know. But yeah, I'll still probably just do Wednesday. I'll probably do it later in the day on Wednesday.
All right.
Yeah. Um, but yeah, anyone have any questions about anything in general? Yeah. Just like an FYI, like, yeah, for the next session, next session is gonna be the last one. Like, really, like, I don't want to just like lecture the whole time because I want you guys to like, come and like talk to me and stuff like that. Because that's how I like learned a lot, like with the chem stuff. When I was in like in AP Chem and stuff like that in high school, I I didn't just like hear the questions and from class and just like practice on my own. Like I also like actively sought out someone that was like my teacher who was smart and like they knew like whatever and they like even though I may not understand it like the first time, after like the fifth time, I actually did understand it by like repeatedly going to her and like asking her questions and whatnot, right? And so like I hope that I can provide that for you guys, because yeah, like come to me and ask these questions. If you're not like confident in whatever, that's okay. And just come and just ask. There's no like judgment or anything like that. And yeah, you do yourself a service by doing that if you're struggling with it. I know a lot of people are struggling, but yeah. Um hmm, yeah. Did anyone have any other questions or anything like that? Okay. Then I guess I'll end early. So I hope you guys have a wonderful day. And yeah, I hope you guys take care. Bye, guys. Good night.
Bye. Thank you.
Thank you, Luke.
See you. Bye bye. Peace out.
Bye.
Peace.
Oh, I just have a quick question. I don't know if you read it in the chat, but
Yeah, I did.
yeah,
Mhm.
so it's a little weird asking in front of everyone. I don't know. It's just like
Yeah,
questions
yeah.
from the exam. So I was wondering if you're free tomorrow. Well, like what times you're free. So if like you want, we can set up a meeting or like if it's easier to just email you the questions. Like I don't know. Because I know you also have finals on Wednesday that you want to study for. So
yeah, no, I can do it sometime tomorrow. I mean, what time's your calc final?
it ends at 2:30. So I think I'll be home by 4.
Okay, so then yeah, I can do 4.
4 is fine.
Yeah, how many questions are it?
Um, it's just like a couple questions. Like actually, we can go over if we can go over one now if you're free.
Yeah, we can do it really quickly.
Yeah, so let me see where it went. Give me 1 second. Sorry, I just had it out, but 4, 25, 20. So it's asking for the Lewis structure for an iodide ion.
Oh, that question. Oh, yeah, I remember that question. I think it was a little confusing, right? What was the answer for that?
The answer is 27 was D. Oh wait, why am I saying 14 non-bonding electrons.
Wait, no, iodide, what's the iodide ion?
IO2, and then it has a negative charge. Negative
Okay,
1. Yeah.
so what was the question? What was the question you said? Well,
It says
um,
the Lewis structure for iodide contains, and then the answer choices are like how like X amount of non-bonding electrons.
oh yeah, yeah, yeah. So yeah, like I was saying, with these kind of questions, they can ask about like the non-bonding stuff. Well, that's basically the lone pairs, right? So let's go through this, right? So there is how many valence electrons are in iodine? That would be 7, right? Because it's a halide. And
Yeah.
how many valence electrons would be in oxygen? That would be 6, right? And then there's negative, right? So that's a negative 1. That's an extra 1 that you add. So it'd be 7 plus 6 times 2 plus 1. So that's 12, 13, 20, right? There's 20 total electrons.
Yeah.
All right. Okay. So there's an oxygen, there's an oxygen. That's one of the things that could be, right? Let's try to see what we can do with this. 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. Okay. So there would be 8, there's 16 total, right? There is 20 total electrons, right? So if there's 16 electrons that we already used, there's 20, you have to put 2 here and 2 here.
Mhm.
So the total answer for this would be not just 4, because there's how many non-bonding electrons, right? So it'd be all the lone pairs, but like times like, because it's not lone pairs, it's the individual electrons, right? So it'd
Yeah.
be wait, did it say like in the minimized, like did it say octet rule or did it not say octet rule?
It says minimized formal charges on all atoms.
Okay, so with the minimized formal charge on all atoms, you would want a double bond on the oxygen, on
Yeah.
both oxygens, because I is a hypervalent thing. So with that in mind, right? Yeah, so this would be the correct like structure.
Okay.
So like with this, it would be, what's it called? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, actually, let me check this before I tell you if this is right or wrong. So, um, one thing to note is like the what do you think? The charge of this whole thing, right? Technically, you would want the oxygen to have the negative charge because it's actually the more electronegative thing. So, I think right now the I has the charge, which might be the problem. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so the I has a negative 1 charge. So while this is technically true, that's not actually a good thing to do. So I think a better thing would be something like this, where it would have a double bond to the O with this being like this.
Single bond.
Yeah, something like this. Because you would rather have an oxygen have negative charge than the I, because O is more electronegative than I.
Okay.
Okay, so now if I were to count this up, it would be 4 here, 4, so 8, 8, 14. Is that the answer
Yeah, 14.
or? Oh, okay, I'm good at my, okay. Okay, that's good. So yeah, yeah, yeah. So I think what probably may have stumped some people on the test was drawing this thing.
Yeah, I think I drew it wrong. That's why. And then it says for resonance structures, it would be 2 resonance structures, right?
Is that the answer?
Oh, yeah, like I didn't check the answer. Yeah, it is 2.
Okay, so
It's just B because you can move the bonds around. Like, I don't know, resonance structures was a little weird for me, but I think it's just because I'm weak with drawing Lewis dot diagrams.
yeah, it's just I think for this purpose, it would be just like moving this so there, because that's all you guys really learned.
Yeah.
So like yeah, in the nitrate ion, that's like the example that he used, right?
Yeah.
All he did was move the double bond to there, right? And then move the other double bond there. So like in the same way, you can just move this there, and then
Yeah.
yeah.
All right. So just like one quick question, like in
Mhm.
regards to this, right? So you know how like all the noble gases have 8 electrons, or is that 8
Mhm.
valence electrons?
Yeah, 8 valence electrons. That's the key
Valence.
takeaway there.
Yeah, and then oxygen has like 2 valence, and iodine has 7 valence.
No,
So
no, oxygen has 6 valence electrons.
oh yeah, 6 valence, but it can make two
Yeah,
bonds.
it favors 2 bonds. Yeah.
Yeah. So okay, wait, what was my? Can I see the diagram again? The Lewis dot thing.
This one?
Yeah. Okay. So when you draw the diagrams, right? You know where the lines are? You would count them as two valences, right? Like I don't know if you
Like the
understand.
bonds? Like the bonds?
Yeah, the bonds
So the bonds, yeah, they count as 2 electrons, but they count for both the oxygen,
and
like,
the
and the
iodine.
iodine. Yeah.
Yeah. So if you would count like how many valence electrons iodine has here, right? It would be the 4 from the non-bonding pairs, and then before then 6, 8, 12.
No, no, no. So, um, all atoms, right? The valence electrons are like set, right? So iodine has 7 valence electrons. That's
Yeah.
just set, right? Like oxygen always has 6 valence electrons. So
Yeah.
like, yeah, maybe I think you're asking me the wrong terminology.
Uh,
So
Oh,
like, yeah.
let me see. Okay. So what I mean is, so if you count, I don't. Okay, yeah. Like, so you see the oxygen on the left, right? So
Mm-hmm.
it has 4 non-bonding electrons.
Yeah.
Then you would count each. Oh wait, actually, never mind. I think
Are
I
you
got.
asking me like formal charge?
No, I'm just asking for electrons in general, but I think the thing is, I think the Lewis dots confuse me. It's because if you sometimes it's like the when you count the electrons in total, right? So there's like 2 bonds on the left. Those would be
Mm-hmm.
like 4 shared electrons, but that would be 2 electrons to oxygen, right? So then it would be 2. Okay, yeah, I kind of got it now, I think.
So like, I think like a thing to note is that with this oxygen, right, it would be something like this fulfills its octet rule. Um, yeah, and 4 electrons for this oxygen are being shared like in total. And then the same thing with here. There's how many electrons are around iodine? There is 1, 2, 3, 4, right?
Yeah.
Plus 6, 8, 10, right? So I think I understand what you're saying. Like how many electrons are around the central atom? Like that's a question that could be asked actually on the test. So
Yeah.
like for this molecule with the minimized formal charge, you would say 10 electrons. Okay?
10 electrons.
For this one, because there's 1, 2, 3, 4, right? And then
Okay,
the
yeah.
bonds are
5, 6,
shared, right?
7, 8, 9, 10, yeah.
Yeah, yeah. So
Okay.
that's a good question you asked because I think that could be a question on your test as well.
Okay, that makes sense.
Mhm.
And then like I don't want to overburden you. If you're not available tomorrow like at 4, that's completely fine. I
No,
can.
I'll be fine for tomorrow. But yeah,
Okay.
I'm gonna get going now because I have something to get to. But
Yeah, yeah.
yeah.
All right. Thank you so much.
Yeah. So I'll see you at 4 tomorrow, okay?
All right. Bye. Have a good night.
Bye-bye. You too.